The wingspan averages about 10 to 12 meters and the chord measures 2 to 3 meters. The chord is the greatest distance between the two edges of the wing. Its surface area ranges from 20 to 30 square meters. The section of the wing in red is called the leading edge. It has openings which air flows into when inflating and then during the flight, hardening the wing into its characteristic shape. The rear section of the wing in the foreground of the image is called the trailing edge. Here is where the upper and lower surfaces of the wing reconnect to form an airfoil. The extremities of the wing are called stabilizers. The surface of the wing on top is called the upper surface. The surface of the wing on the bottom is called the lower surface. The hollow space between the upper and lower surfaces is separated into several cells by ribs. The openings we see here are used to inflate the wing. The circulation of air between cells is made possible by holes in the ribs. Near the leading edge, the fabric used for the rib is much more rigid. Nylon or polyester threads are meticulously stitched to make the fabric flexible and light, while at the same time extremely resistant. The wing is connected to the harness by carabiners. These carabiners are considerably oversized and can withstand weights exceeding 2,000 kilograms. The harness is where the pilot sits. The first noticeable element of the harness is the compartment sticking out on the side. Known as the container, this is where the reserve parachute is located. The reserve parachute's deployment handle, here in red, is located at the top of this pocket. The parachute straps leading out of the container are anchored to the harness near the shoulders using carabiners. On the back of the harness is a storage compartment. This compartment is usually used to store your paragliding sack during the flight. Also located on the back and bottom of the harness is the bag protection. There are two main types: airbag protection or, as shown here, foam bag protection. The pilot sits on this seat board inserted in the harness, which makes it comfortable and allows the pilot to transfer his weight to control the wing. How do we obtain the relative airflow necessary to create lift when there isn't any wind? By simply transferring his weight to the wing, the pilot pulls it towards the ground, forcing it to move forward through the air. This movement we call airspeed, and this creates the relative airflow required to produce lift. Altitude, therefore, is the paraglider's energy reserve, and by using our weight to draw on this reserve, we're able to fly. A wing is always inflated facing the wind. Facing the wind, you'll find it much easier to obtain the relative wind needed to create lift. It will also make shorter launch distances possible, which can be useful for certain sites. When launching, several different scenarios are possible. A headwind, the ideal situation. Using this configuration, orient your wing so that it's facing downhill and into the wind. Situation. In a calm and stable air mass, without lift, sink, or wind, the paraglider's trajectory will not be disturbed. It'll approximately fly at the speed specified by the manufacturer. The same applies to the sink rate, which also figures in the technical specifications. In this example, the ground speed and the glide ratio are roughly the same as the airspeed and the lift-to-drag ratio. Second example. The paraglider is flying into a 15 km/h headwind. In this case, the horizontal ground speed is reduced. It can be easily calculated by subtracting the wind speed from the paraglider's airspeed, since they are moving in opposite directions. 37 minus 15 equals 22 km/h. Though its ground speed has decreased, the paraglider still falls at the same speed. Thus, for the same altitude, it runs a shorter distance. Its glide ratio has decreased. A new example. The headwind is now 35 km/h, almost the same speed as the paraglider, which, by the way, could end up being rather dangerous and should therefore be avoided. In this case, the ground speed is almost zero. The paraglider continues to descend at the same speed and appears to be falling vertically. Know how to get your bearings and observe these phenomena. Adapt your flight plan accordingly so that you're sure to make it to the landing field. An S-turn landing approach allows the pilot to lose altitude by making a series of S-turns within a cone of safe airspace. The size of the S's decreases as the pilot loses altitude. By tracing smaller and smaller S's, the pilot loses enough altitude and lines himself up with the target for the final approach. When using this technique, turns need to be smooth and steady. Make sure you avoid steep turns near the ground. A series of figure 8 turns are used to lose altitude. The 8s get smaller and smaller so that the pilot can lose altitude and get in line with the landing field before his final turn. If the pilot overshoots the landing, he can trace different sized figure 8s to reposition himself. Let's go over the rules of priority that prevent paragliders from colliding. The prime rule is the following. It's the pilot's responsibility to take all possible measures to avoid a collision with any other aircraft. The animations that follow present the collision avoidance rules. They are not to scale. Try to maintain a safe distance from the other aircraft. First situation. Two paragliders are approaching head-on with a risk of collision. In this case, both aircraft shall alter course to the right. In case of hill or ridge soaring, this rule is modified. Two paragliders are approaching head-on when ridge soaring. The pilot with the ridge on the left should move out so that the other can maintain course without having to turn into or over the ridge. New situation. Two paragliders have converging courses. When two aircraft of the same classification converge at approximately the same altitude, the one with the other on its right shall give way. On the right is in the right. In flight, if you come across a situation like this, act as quickly as possible. It's pointless to wait till the last minute before reacting, moving out of the way and scaring both yourself and the other pilot. Because each wing has its own technical specifications, your paraglider may fly faster than others. Passing someone is permitted. Internationally, passing is typically done on the right. The aircraft being passed has the right of way, except in Italy where the glider overtaking has priority but must allow enough safety clearance. The glider being overtaken gives way, avoiding any change in direction that might interfere with the overtaking glider's path. Also, in England and in Italy, in free space away from a hill, paragliders can pass on the left as well as the right. When ridge soaring, a paraglider overtaking another glider that is flying in the same direction should pass between the ridge and the glider being overtaken. If you're overtaking the pilot and there is no room to pass, just turn back. When thermaling, the first pilot to enter a thermal establishes the required turning direction in that thermal. All paragliders joining shall circle in the same direction as any other gliders already established in the lift. When an air mass cannot go around an obstacle such as a mountain but is forced to pass over it instead, the wind that climbs up over the obstacle creates a dynamic lift. Unfortunately for us, all obstacles and the airstreams they generate do not create exploitable dynamic lift. In order to create good dynamic lift, 3 conditions are required. First off, the airstream must be as perpendicular as possible to the obstacle. Secondly, the wind mustn't blow too strongly, otherwise it'll become turbulent as it travels uphill. Lastly, the shape of the obstacle. The shape of the obstacle is essential because the air will always find the shortest means of overcoming the obstacle. In the case of this conical hill-shaped obstacle, the wind follows the most direct route around its sides. In the case of a sufficiently wide and reasonably high landform, the wind stream climbs over it and lift is produced just before its summit. Let's look at how an airstream advances uphill and downhill. It's important that you understand this phenomenon, not only to make better use of the lift, but also to avoid the hazardous areas. A lift originates on the windward side of the mount near its summit. The higher you ascend in the lift zone, the weaker the lift becomes. To take advantage of the lift, you should make figure 8 parallel to the ridge, making sure to turn with your back towards the elevated ground. On the leeward side, things are completely different. The airstream does not create upward lift, but rather downward moving air currents that are very turbulent. The further you descend into this zone, the stronger the downdraft becomes. The presence of turbulence makes flying in these areas extremely ill-advised. Thermal lift is another way to make your flights last longer. Warm, invisible air masses of different sizes will lift and carry paragliders up into the clouds. We're not going to give you a detailed technical explanation on how to take advantage of a thermal lift, nor how to fly in thermal lift conditions. However, we do want to provide you with some essential information that will be useful to you later on. How are thermals formed? Remember back to the different energy transfers we discussed earlier? Thanks to radiant energy from the sun, the ground is heated up. It should be noted, though, that this depends on the terrain. For example, a ground covered with snow will reflect more than 3/4 of the radiant heat as opposed to absorbing it. Afterwards, the ground will conduct its accumulated heat to the air directly above it. That heated layer of air will become warmer than the air around it, and as it warms, it becomes less dense and inevitably rises through convection. A difference of 2 degrees is all that's needed to make this pocket of warm air rise. If certain pressure and humidity conditions are reunited, a cumulus cloud will form at the top of the lift. As soon as the lift stops, the cloud is no longer supplied and it will eventually disappear. For paraglider pilots, the cumulus is the king of clouds.